there is an equilibrium between NO2 and N2O4 and NO2, right? So what is there? N2O4 is a gas which is colorless, and we get to see this N2O4 only at low temperature, right? And this NO2 gas, it has a reddish brown color, and we get to see at high temperature, and at normal temperature there occur a equilibrium, right? So what is going to happen, what I am doing is I am taking a closed container in which I am taking NO2. So that means I have taken 2 samples in which I have taken the same gas that is NO2. So what I am going to do, that I am just going to seal it. So I am just sealing these containers, right? Now what I am doing is I have taken a container, 3 containers you can say. So first I am taking 2 containers, right? So in one container what I have put the boiling water, and the other container what I have put, what does it look like? Yes, you are right, it is again a solid form of water, that is the ice, right? So in one beaker I have taken the boiling water, and the other beaker I have taken the ice. And what I have done, so I will just name it with A and B. Say it is a A flask and it is a B flask. They don't have any difference between them, both of them contain the same gas, right? So what I am doing, suppose I am keeping this A flask into a container which has the boiling water, right? And I am just keeping this flask into a container which has the ice, right? So what earlier the constituent which is present in this beaker is only NO2, as I have told you that I have filled these containers only with NO2, nothing else is there, right? So I am just keeping it in boiling water and I am just keeping in the ice for a few minutes, you can say. You know what changes you will observe when you will keep them here? Earlier they contain the same gas, they look similar to each other, but when we keep it in the boiling water and when we keep it in the ice, we get to see difference in the color, you can say. So what happens with the passage of time, what I get to see that in the vessel which is placed in the boiling water start you can say the liquid or you can say the gas which is in the NO2 the NO2 which is present in the boiling water start turning reddish brown. This we get to see the vapors color reddish brown, right? And this reddish color just deepens, that means becomes darker. So these observation I saw in this one, the container which has the boiling water. And what do I get to see in the vessel which, or you can say the container, I am using the same word, don't get confused, vessel or container, I am just talking about the same thing, that we took a vessel which was sealed and it was earlier containing the NO2, right? So what happened to this vessel which is kept in the ice beaker? So what we get to see that it almost becomes colorless, there is no color. Now the reason behind this observation, you know what's that? It's that we know that at high temperature which gas is favored? NO2. So that means this earlier it was NO2, but when it was placed in the, you can say the boiling water, the vapors just start moving more faster and the color, they start mixing into each other so completely that the color of reddish the brown just deepens, just become darker and darker, right, in the boiling water. And in case of the vessel which I kept in the ice, it favors the existence of which gas? N2O4, and as I told you, it is colorless. So that is why we get to see the colorless, it almost becomes the colorless. Now what, so that means that is sure that here it is NO2 present, right? Only the intensity of NO2 has been increased because it is placed in the boiling water, and we know that high temperature just favor the existence of NO2. That is why the color gets deepened, right? Now what is happening in the second one, or what is contained in the B flask? It is obviously a N2O4 the gas, because we know it is favored, its existence is favored at low temperature. And what temperature can be lower than the temperature that is lowered by an ice, right? So that is why it becomes almost colorless, which is the property of N2O4, right? Now what I am doing next, just look at the board. I am just taking another beaker, right, which contain a water at at 25 degrees Celsius. Suppose. So what I am doing, I am just removing this vessel A and I am just removing this vessel B, right, and I am just putting these vessels into the same flask. So this is my vessel A and this is my vessel B. This I removed from the boiling water and this I removed from the ice. And earlier what happened, it has deep reddish brown color and it is almost colorless, right? So what observation now I am going to see when I keep in the container which is at 25 degrees Celsius, which contain the water at 25 degrees Celsius. See that what change I look for that is visible in it, that is the A color, the A tube which was earlier has the deep reddish brown color start fading its color. Its color starts fading, means the color of the reddish brown color start becoming fainter. It is just losing color, it is becoming lighter now, right? And what is happening to the B tube? B tube was almost colorless, as I told you, it was colorless, right? So what happens when I kept in this, that it starts, you can say the color of this colorless the vessel just start, you can say, imparting a lighter brown color, lighter reddish brown color. So why they are doing so? Because at 25 degrees Celsius they exist in a equilibrium. That means there exists equilibrium between the N2O4 gas and the NO2 gas. And I think it's now clear, it's completely clear to you that how temperature just affect the, you can say, the equilibrium, because as I kept in this, then this NO2, when there was only NO2 and I kept beaker in the boiling water, so that means it got shifted to the it becomes more intense in the boiling water, right? But when I kept in the ice bath, then it turns into the N2O4, because at low temperature N2O4 is favored. And when I just removed them and kept in the vessel which contained the water at 25 degrees Celsius, there exists an equilibrium between the two. That means there you can say and you know what you get to see after passage of time. The almost see the color of reddish brown start becoming fainter. In it starts from colorless to becoming lighter brown. But after you can say few minutes or something like that, the two tubes will have the same color, which shows there exists an equilibrium between the N2O4 and the NO2. They both will impart the same color, you can say the light reddish brown color, not the darker one, only the light one, and the same colors of both the tubes. So that means this just proves that there exists an equilibrium between them at 25 degrees Celsius. So this is how you are going to explain the second factor of the which affect the equilibrium, or which just shift the equilibrium in forward or a backward direction. So this was the temperature factor, right? Now we will be doing the third factor. I am just summing up the factors so that you should not get confused, right? So what are the factors actually? Two we have already done. So what were the factors? The first factor which we discussed was the concentration, and you are clear with it, right? The second factor which I explained you was temperature, right? Now the third factor which we are starting is the pressure, right? Now I am just talking about the pressure. So before we start with the pressure, you should be clear in your mind that the pressure will not affect the equilibrium under two conditions. Otherwise it will affect, obviously it is going to affect the equilibrium. But under two conditions, the pressure, the alteration in any kind of pressure will not affect the chemical equilibrium. And what are those two conditions? One is that if the reaction do not involve any gaseous component, the pressure is not going to affect the equilibrium, right? So the first factor, if the reaction do not have any gaseous component, so that means no change in the equilibrium is going to happen if we change the pressure, right? And what is the second factor? The second factor is that if somehow in some condition the moles of the gaseous moles of the reactant and the product are equal, then again means delta N is 0, because delta N we calculate by subtracting the moles of product by moles of reactant. And as I told you, if in any condition the mole of the product and reactant are the same, so that means delta N is again going to be 0. So under that condition also the pressure is not going to affect the equilibrium, right. So these are two factors. One is that the reaction do not involve any gaseous component, and other factor is that when the number of gaseous mole of reactant and product are same. So under these two conditions the pressure will not affect the equilibrium in any case, right. It is going to affect the chemical equilibrium only if the number of gaseous moles of the reactant and product are different, right. So this should be clear in your mind, because when you get some reaction, if the moles are equal and if it does not involve any gaseous component, so strictly right that yes, the pressure has no effect on it. But if there exists a difference between the number of moles and it do involve the gaseous component, the pressure is definitely going to affect it, right. So see how pressure is going to affect. Suppose for this I am taking an example. I am not taking a general equation because here we need a mole also, so we need to balance the reaction as well. So I am taking a particular example. See, so this is the Haber's process, right, you know that. The nitrogen gaseous, again a gaseous component, again the gaseous component hydrogen, this forming the ammonia, 2 moles of ammonia, again the gaseous component. So obviously you get to see that as I've told you, these are the two factors which we get to see. If delta N is 0, then the pressure is not going to affect the reaction, and moreover if it does not involve the gaseous component, then also pressure is not going to affect it. So it involves the gaseous factors. The first factor we have already just cleared, and the second factor is that we get to see that in this example which I wrote, the number of mole of product is equal to the reactant. So that means the example which I took will not be affected by the change in the pressure, right. So I am taking some other example, right, like I'll take an example, like I'll take a general example. Suppose I say that I have this kind of reaction, right. So in this you get, and these are gaseous components, right. So I'll write here in order to avoid any confusion, right. So what is there? It is a gaseous component, that means it will get affected due to the pressure factor, right. And the second is that the moles of reactant and product are not equal, right. The product moles are 3 and the reactant side moles are 2. So that means this reaction is going to affect by changing the pressure. Now we will just look at how the pressure is going to change this equation, or how it is going to affect the side at which it is going to be more favored, right. So what happens? In the first case, what I am doing, I am increasing the pressure, right. So if I am increasing the pressure, what do you mean by increasing the pressure? Increasing the pressure is force per unit area. That means we are just making the molecules more closer, because more closer the molecules will be, more they will exert pressure, because the pressure is actually ultimately the reason behind is that collision, and for the collision to occur they just need to come closer, right. So when I am increasing the pressure, so automatically it should strike your mind that yes, that the pressure is increased, so automatically that means volume is decreased, because pressure is increased only when the particles come closer, and when they come closer, so automatically the volume will decrease, right. So the pressure I am increasing, what will happen? The volume will get decrease. Volume get decrease, what does it mean by it? That means volume decrease, that means moles per liter are more, there is more concentration, that means the moles of gas present per liter of the solution is just now increased. That means molar concentration is increasing. So I think it's clear. See, I have just altered this factor, automatically this factor got altered. I have increased the pressure, so volume gets altered, how it decreases, and it just increase the molar concentration as well. So what is going to happen in this case? So obviously the reaction is going to favor more. If I say that molar concentration is increasing, that means the moles per liter are more now. So obviously the stress is that the moles per liter has just risen up. That means, or you can say they have just increased, that the number is just increased. So automatically the reaction is going to shift in that direction in which the lesser moles are present, or where you can say the molar concentration is decreased. So in this case automatically, like I have told you that molar concentration is increasing, that means the reaction, that side of reaction will be favored which contain less number of moles, because we need we have to reduce the stress of higher concentration, molar concentration. That can be done by shifting the reaction that side which contain less number of moles. So as we can look in this example, which side has less number of moles? This has 3 and this has 2, because if nothing is written on in front of any alphabet, that means 1, right? You know that. So here is 3 and here is 2. So that means which side will be favored? Which contain lesser number of moles. So that means the backward reaction is favored. And the same way, if I am just decreasing the pressure, it will affect the volume, that it will increase the volume. When the volume is increased, how it is going to affect the concentration? You are right that the concentration will be affected by that molar concentration, moles per liter will now decrease, and the reaction will just shift into the direction with the moles per liter is increasing. So obviously if I will decrease the pressure, the reaction which will be favored will be the backward. So this is how you are going to explain the pressure factor. Just keep in mind, this pressure factor won't be applicable under 2 conditions. I am repeating again and again just to make you understand. The first factor is that if the reaction do not involve any gaseous component, the equilibrium does not get affected by the pressure, right? And if there is no change in delta N, that means the number of moles of product and the reactant are equal, then also it will not affect by the change in the pressure. Otherwise, in any condition, the pressure is going to affect the equilibrium, right? So this is the third factor which we have discussed. The fourth factor which we will be discussing will be addition of inert gas, right? You know what are inert gases? Yes, you know, we have already done with the atomic structure, and you know that what the inert gases are. Inert gases are actually those gases which have stable electronic configuration, like helium, neon, argon, krypton, xenon, like that, right? So, and what we are just studying that if we add any kind of inert gas to a chemical reaction, so how it is going to alter the equilibrium. So this is the fourth factor which we will be discussing. I am just writing here, look at the board carefully, because before we start with the fourth factor, one thing should be clear in your mind, that we can add an inert gas. Obviously we can add an inert gas, and we can add this inert gas under 2 conditions. One is at constant volume and other is at constant pressure, right? So the fourth factor is that the addition of inert gas, right? So addition of inert gas can take place under 2 conditions, as I told you, at constant volume and at constant pressure, right? So first condition which we are seeing is that I have an example of reaction A plus B, again a general reaction. So I am just adding an inert gas to it at constant volume, right? I am just adding this inert gas at constant volume. So that means whether I increase, you can say, when I add this inert gas to a reaction, the volume is not going to be altered, right? Because it is occurring at constant volume, right? And if it is occurring at constant volume, that means volume is not going to be altered, then obviously the concentration is not going to change. And if the concentration is not going to change, that means the addition of inert gas at constant volume is not going to affect the chemical equilibrium. It will not, you can say, support the forward reaction, and it won't support in the backward reaction. So whenever you are adding inert gas at constant volume, the concentration is not going to change and it will not going to affect the equilibrium, right? And what happens when I add the inert gas at constant pressure, right? So that means when I am adding at constant pressure, that means the volume may increase or volume may decrease, right? We are doing at constant pressure, the volume might increase or volume might decrease. And what happens when volume increase? We know that when the volume increase, the concentration, the molar concentration decrease. Molar concentration decrease means moles per liter are less now. So they will just shift the direction as we did in this case. They will just shift the direction in that case in which the moles per liter is increasing. That means the side which has more number of moles, and vice versa if we decrease the volume in this case. So when we are decreasing the volume, what is going to happen? The molar concentration will increase. That means mole per liter will increase. The similar way that like it happens here, right? So that means the molar concentration is increasing. Molar concentration is increasing. That means moles per liter are more now, and the reaction is under the stress that the moles are just you can say just increased, right? So it will just shift the direction. In that direction will be favored in which the stress gets reduced. That is, the number of moles gets reduced. So that means which direction will be favored? The direction which contain the lesser number of moles. So this is how I have told you that how the chemical equilibrium is just affected by the factors, and how the Lee-Chartley principle just explain that how the stress can be reduced. Either the stress is in the form of concentration, temperature, pressure, and addition of inert gas. Don't forget that we can add inert gas under two conditions: constant volume and constant pressure. Constant volume is not going to affect the equilibrium in any case, but at constant pressure the volume may increase or decrease, and likewise it is going to affect the side, the reaction, or you can say the forward or the backward reaction. It will be supporting any reaction, whether it can be forward or whether it can be backward.